Now that we have seen what a parametric curve is, we can start asking some calculus kind of questions. Of course, we've already looked at those questions last time when we looked at how to apply limits to parametric curves. But what we're going to be looking at this time is slopes. How can we figure out the slope of a parametric curve at its points? So first of all, by definition, recall that the slope is going to be given by the derivative of y with respect to x. But notice that now y and x are our usual good old dependent and independent variable in the traditional notation of a function. Now, in this case, when we have a parametric curve, x and y are themselves functions of t, and in fact, most of the times when we need a parametric curve, we don't have a way of knowing what y is as a function of x. Yet we have a graph and we have some points and we have tangent lines on those points here and there and everywhere. So it makes sense to compute the slope. How can we do that? Well, pretty much by using an old trick. In this case, in fact, what we have is that we're looking for dy by dx, and we're going to use the good old trick of multiplying and dividing by the same thing, or in this case, dividing top and bottom by the same thing, namely dt. Now, if you remember, this is an operation which needs to be checked out, because what the symbol dy dt, just like the symbol dy dx, do not really indicate fractions. They indicate just the derivative, which is the limit of a fraction. But as usual, someone has checked that in fact it works in this situation. And so we can do that. And so what that means is that in order to get the slope of a parametric curve, all we need to do is compute the derivative of y with respect to t, put that on the top of a fraction, compute the derivative of x with respect to t, put that in the bottom of the fraction. You can see that. Might as well use my cursor here since I have it. So this is what we're going to put on top, the derivative of y with respect to t, corresponding to the fact that we have a dy in here. And on the bottom we have an x prime, so the derivative of x with respect to t, corresponding to the fact that we have a dx in here. Okay, so sometimes when you're going to see the physics style notation, which is a little bit shorter. I certainly like using it simply because it is short, but other people may do that as well. And that is, instead of writing y prime x prime, since we're taking derivatives with respect to t and we can think of t as time, we can write that as y dot over x dot. So when we have a dot on top of the variable, that means we're taking the derivative with respect to time. You may want to use that also for related rates problems. Now, notice one important thing here. What we are after, what we're seeking, are derivatives with respect to x. We're looking for dy dx. We're looking for the slope, right? So we're looking for the geometrical slope, which is given by the derivative of y, vertical variable, with respect to x, the horizontal variable. However, what we're actually using is derivatives of both of them, x and y, with respect to t, to the extra parameter. Okay? So try not to make any confusion between the two. We're going to see lots of applications, well, lots. We're going to see some applications in class, and I trust you're going to see some more on your own. But again, it's important to keep the two separate and understand which one you're dealing with, whether derivatives with respect to x or to t. The idea of distinguishing between the derivative with respect to x and the derivatives with respect to t comes in quite importantly when we're trying to figure out how to identify concavities on a parametric curve. Okay, now don't jump on me. We haven't done concavities in the course yet, but you have taken Math 31, so you do remember that concavities are really something that comes from the second derivative. Okay, so what we have to do is we have to try and figure out how can we compute the second derivative of y with respect to x when in fact all we have is x and y as functions of t. Well, we figured out how to do the first derivative, so all we have to do is the second one. Remember that that second derivative is just the derivative with respect to x of the derivative of y with respect to x. Well, we know what the derivative of y with respect to x is. We've just seen that that's y dot over x dot. So what we need to do is we need to take d of y dot over x dot divided by dx. Well, that's not as simple as it seems, because of course again x dot and y dot are functions of t, and we're trying to differentiate those in terms of x. But we're going to use our good old trick of dividing top and bottom by dt. So what do we have on top? On top we have the derivative of y dot over x dot with respect to t. Well, that's fine and dandy because x dot and y dot are functions of t, so we can take their derivatives with respect to t. And on the bottom we have once again dx dt, which is going to be our x dot. So all we need to do here is remember that on top we have to compute the derivative of a quotient, and so we need the quotient rule, but we know how to do that. So the derivative at the top is going to be given by the derivative of the top of the top. Oh, let's not make a confusion here. So we're taking the derivative of this quotient. So we're taking the derivative at the top with respect to t. Remember, everything now is with respect to t. So that would be y double dot. So second derivative of y with respect to t times the bottom minus the derivative of the bottom again with respect to t. That gives us x dot times the top. That's y dot, all divided by the bottom, x dot squared. Now that only takes care of the numerator, so we still have to divide by dx dt, which we're going to do by multiplying by 1 over x dot. So all we need to do now is put those two denominators together, and we end up with, hey, this looks better. These dots look a lot better. Hey, I'm glad I found it. Alright, so what we end up with is something that looks very much like the quotient rule, right? Except it's not, right? It's a second derivative. And once again, we're taking the second derivative of y with respect to x by using x and y both in their formulations as functions of t. So we end up with something that looks very close to the quotient rule, but is not. And also notice that in the bottom we have an x dot cubed, not the x, the usual denominator squared that we're used to. So once again in class we're going to use this formula a few times, and we're going to see how that applies and how we can interpret it and so on. Keep in mind again, we're just getting a first encounter with these parametric curves, so the examples that we're going to use are going to be fairly simple ones, and the kind of depth to which we're going to go with applying these ideas is also not going to be very deep, but it's just to get our feet wet and try to figure out how these derivatives work. Remember, main problem here, distinguish the derivatives with respect to t from the derivatives with respect to x. And then if you can do that, then you're probably going to stay away from major troubles.